Hello, welcome to the BioPharma Finder help video. In this example, I'm going to show you how to process subunit analysis data using the Intact workflow. So here's the BioPharma Finder 2.0 homepage. So we're going to go to the protein sequence manager, and I already have the Intact full molecule in the software. So I have here you have 4 chains. And you can see that I have 2 max modifications. So this FASTA file or protein sequence would be great for the Intact molecule. However, to do the subunit analysis, I need to bring in the individual parts of the molecule as separate sequences. So let's go ahead and hit edit. Let me slide this over here. Oops, sorry, not edit. New. So we need to bring in a new version. Okay, here we go. So you can see the screen. So we can import. You can import a FASTA file or you could paste the sequence. So let's bring in the light chain. So here's the light chain, and I'm going to assign this to an Intact category. And it does not have any modifications because it's reduced. And this is the mass that will be searched. So for Intact analysis, the target protein mass is what gets searched when you actually do the annotation. So you cannot bring in the heavy chain and light chain in order to be able to identify just the light chain region. So that's why we have to bring these in as separate. So I'm going to save, and then I'm going to import the FD region. It also does not have any modifications. So I'm going to assign it Intact for this specific protein, save. And now let's bring in the FC. So the FC has the glycosylation. So this site right here actually is glycosylated for this protein. Now I can do this in 2 different ways. So I can, and also when you come over, we had feedback in the past that people would have a hard time finding the CHO or the glycan feature. So what you can do is several things. If your monitor is too small or your resolution is not enough, you can expand this window so that it maximizes your screen and you should be able to see all the information. You can also use these to close and open the windows, so that might help. And then we also have a little scroll bar here that you can scroll to the bottom. So the N-glycan is actually at the bottom, so if you want to search the entire CHO database, you could set that to CHO, and then I will save this as a CHO. But I could also, if I want to do more of a targeted search, I can just apply the individual glycans as variable modifications, and I can save those. So when I do this, I say variable, and then I can save it. But do not use these in peptide mapping. So you do not want to assign the glycans as variable mods in peptide mapping because the software does not know that it's a glycan. The only way you can do it in peptide mapping is to actually use the CHO or the human database. And the reason is when you do this, when you tell it to do CHO, if it thinks it's a glycan, it's actually going to look for the glycan fragments in the MS2 spectrum. When you assign it as a variable mod, it doesn't know to look for the glycan fragments. So for peptide mapping, you want to use the databases. For Intact, you can use either or. Okay, so save. So now we have all of our sequences in the software. Now let's go to the Intact homepage. So here's the Intact homepage, and we can start our new experiment. So let's call this subunit, and let's browse for our raw files. And in this example, we have 2 technical replicates of the IDES digest. So I'm going to assign a condition for these, and the reason I'm going to do this, and I'm going to assign them both to the same condition, is I wanted to actually do the CV calculation for the abundance so I can see the variation in my 2 raw files. Since I have 2 raw files, I could choose between batch processing and multiconsensus. I'm going to select multiconsensus in this demonstration, and that means that it will process the individual files and it will merge together the results from those individual files into one result. Now you could also do batch processing where it will process them individually and then the results will be kept separate. Okay, So in peptide mapping, or in here in intact, sorry, not peptide mapping, I can actually select more than one sequence. Peptide mapping, you can only select one. So I'm going to select my three subunits. And I know that to choose the processing method, the first place I always often think is, what kind of data do I have? Do I have isotopically resolved data, or do I have unresolved data? And so this, it's actually resolved. So I'm going to use the extract algorithm. So what I can do is just type in here, and these are all my extract methods. So once I have that, we do provide you some default methods. So these are the three different default methods that we provide you. And what you want to think about next is, how do you want to get your source spectrum? So in the deconvolution software, the first step is get a source spectrum, then deconvolute it. So you really need to choose the best way to obtain your source spectrum for your data set. And so since this file has three different molecules, it has a light chain, the FD and the FC, I'm going to want something that can process and determine multiple peaks. So I have two choices. I could do auto peak detection, or I could do sliding window. So let me just show you, I'm going to pick this, and I'm actually going to do edit method just to show you a schematic. Now, you don't have to do edit method, but I'm just going to want to show you this schematic so you can see the differences. So here under the component detection in the edit method parameters page, you have this page. And so you start with your chromatogram parameters, you have your source spectrum selection, and then you have your deconvolution. And then over here you have an interactive chromatogram that you can toggle back and forth. You can do averaging, so I can create an average spectrum. I can zoom in and out, toggling back and forth between this. And I do see the different files, so I can see both of my raw files as well. This also can be popped out. It's floatable, and you could copy and paste from here as well. So you see the blue integrated areas on the chromatogram, which you saw in the old software. And that's because we're doing the auto peak detection. So if we do auto peak detection, the areas in blue are what it will actually, the areas that it would actually go through, create the source spectrum. Oops, let me show you. So it would create, so basically the software is going to go through and average across this time range. It would take this source spectrum, deconvolute it, and it would do the same thing for these other ones. Now you cannot adjust this in like you do in Qual Browser in the software. It's not a parameter that you can actually, it's not something you can adjust. There are two parameters for this. So you have the sensitivity, which is up here, and then you have relative threshold, which is also here. So you can find two of those parameters. The other option you have, now average over RT, let me just explain what this is this is where you define the time range. So you say, okay, I want it to be right here. So if I wanted to look just at the light chain, I could draw, and it's going to take, here's your source spectrum, and it's just going to deconvolute that source spectrum. You can also enter the time range over here, and it will define the red box that way as well. So that's going to show us one peak at a time. So we really probably don't want to use that one. Our other choice will be sliding window. And I'm going to explain in more detail how you use sliding window when we actually run the software. It's easier to show in the actual live demo. Here's your parameters for the extract algorithm. You can also adjust the parameters for respect. We have an identification tab, and this is where you have your protein sequences. You have your match sequence, so you have to have a tolerance to match the masses here to your deconvolve values. So that's what this is for. We're not going to do DAR or antibody to drug ratio in this example, but I will have another video for that. One parameter that you do want to look at, because we have multiple files, is the multiconsensus component merge. What that means is, think about how this works. So we have two different raw files. We're going to deconvolute both of the two different files. So we're going to have two different results. And imagine that you were doing that and you exported those results out to Excel. So now in Excel you have two different Excel sheets with two different results from your two different files. Now you want to merge those together. And so you're doing this in Excel. And what you would first do is you'd have some mass tolerance to say whether the two masses are the same. So that's what the software has. The second thing is you would look at the retention time. Are those within a certain retention time window? And so that's what you have here. And then finally, what we're doing also is we're saying, well, how many files does it have to show up in to be considered? And so if we only have 2 files and we only want to see things that show up in both files, we set this to 2. But if we want to allow the software to show us things that are only on 1 file, we can set that to 1. Okay, so that's how these parameters, and this really only applies when you have multiple files and you're doing multi-consensus. So reporting is the same that was in the old version of the software. However, this only applies to single file experiments, and it will not work when you have DAR enabled or multi-consensus experiments. That's a limitation that we have right now. And then you can save your method, if you want to use this method to process other data files. You can export out your parameters to Word and Excel once you have everything fine-tuned. So I'm not going to save this method because it really didn't change anything. So one thing that I like to do is I like to use the manual processing. So let's filter this back so we can look at our, there we go. Now you'll notice when I have extract, auto peak detection, I can't do manual processing. I can only add it to the queue. Okay, so let's go ahead and just do that. Let's let it add it to the queue and see how the auto peak detection does. If I do this, it's going to pop up a message. And this message is telling us that if you're going to do auto peak detection, you can't do multi-consensus. So we have to do batch processing. So meaning it's going to process each file individually, and it will give you the results for each file individually. So let's do auto. We'll do auto. We'll name that. Okay, so let's go ahead and submit that to the queue just so you can see how that works. Okay, so now we have our 2 different raw files. It's running, and it gives a timestamp and date so that you know that these 2 files were processed together. So you'll be able to go back and look at the results. So that's in our queue. So let's go back. All right, so we have those in the queue. Now let's do the multi-consensus. And in this case, I'm going to get rid of the auto after our name, but let's do multi-consensus. And for simplicity, let's just do that because it's easier to find. So we did that one last time, but now let's do sliding window. So now that we've done sliding window, you'll see that the manual has opened up. And you could also do manual with average over RT2, and you can add these to the queue. So there's just a limitation when you do auto peak detection. You can only do that in an automated way. So let's do sliding window, and we're going to go processing. Now, when you're in here, we're in the process and review page, you have this thing called real-time optimization, and that allows you to access all the parameters that we just looked at the previous page. So all the parameters and everything's here. So you don't have to leave this process and review page to be able to fine-tune all your parameters. So just know that because it helps you be able to assess and define and come up with a really good processing method that you could later use to process other data files. So what I often do is I start with the chromatogram parameters. I'm going to look at the mass range. Now, when you have this set to sliding window, you can click in here, but you're never going to see the source spectrum because the sliding window is actually going to generate the source spectrum. So if you want to be able to see that, you can just toggle over to average over RT, click, and then go back. So now you can actually see the source spectrum. All the windows are floatable, so you can pop them out and move them in, and so you can see everything a little bit easier. You send them on different monitors as well. And so we can assess the RT range, and I think that's probably okay. We could even set this maybe 700 to 1700 or something. We can change this. Now this mass range affects the chromatogram, but it also affects the deconvolution. So this is the mass range that's being considered for your deconvolution. It's really important to remember. Okay, so let's go back to sliding window because that's what we're actually going to do. And now let's zoom in, and I want to start this. It's going to take a long time to process, so I'm going to explain it as it's processing, and then I'll probably stop it and show you one I already processed so you can actually see the result. But I want to explain it live because it makes it so much easier to see what it's actually doing. Okay, to do that, let me put this window back over here. Okay, there we go. And there. So we'll be able to see what it's actually going to do when it's running. So the first step in figuring out your sliding window parameters are define your retention time range that you want to process. Now I could process this whole entire run, but I don't need to. And extract sliding window is a little bit slower than respect, so you probably just want to narrow in exactly what you want to process. So what we're going to say is let's do 5 minutes to 8 minutes. So that's going to be a total of 3 minute time. Now the second parameter is the width. So this is how wide is your window going to be. And half a minute is what we're saying. So if I did that and I drew a little box, it would be that wide. Okay, I think that's a little bit too wide for this data set, so I'm actually going to not use that value. I'm going to change this to 0.1. So I'm going to set this, to 0.1. I'll leave that set to 25. This is the offset between the windows. So again, what it does is it draws little windows, okay, and it's going to average in that window. And when it averages, it's going to get a source spectrum. Okay, and when it gets the source spectrum, you'll have it here, you'll see it here, it's going to deconvolute it. And then it's going to move. And then it's going to do it again. It's going to average, deconvolute, and it'll move. And do it again, and do it again, and do it again. And it does it in this time range. So what you end up with is a whole bunch of deconvoluted spectrum. And then it needs to merge those together into one result spectrum. And so the same way we're merging together the results for the multiconsensus, it's going to merge together the deconvoluted spectrum. So there's got to be a mass tolerance. There's got to be a retention time gap. And in here, we're requiring it to show up in 3 different intervals or 3 different windows for a mass to be considered real. Okay, so let's let it run, and then I'll explain it as it runs, and it might make a little bit more sense too. Okay, so now because I changed the time width of the window, it's going to give me a new recommended value for the offset. So I'm going to say go ahead and run with that. All right, so let's watch it. So here's the window. See how it moved? Okay, see it's moving. So what it does is create, and I have the windows moved around a little bit, so it's creating a source spectrum. For that source spectrum, it's going to deconvolute it. Here's a source spectrum. We're going to get a deconvoluted spectrum. So see how it moves across there. So across this peak, we're going to have, I don't know, maybe 10 windows. I mean, if I sat down and did the math, I'd figure it out exactly. Okay, so as it moves along, it's creating a source spectrum, deconvoluting it. Now, what I find very useful is to watch this. So if there's something you really know that's in that peak, you can really watch the 2 different windows and see if it's actually getting your mass and seeing how it's actually doing it. Now remember, we're going to get a whole bunch of these, and when it gets to the end, it's going to merge them together into your single result file. Now you will see a source spectrum for this peak, a final result deconvoluted spectrum for this peak, and a final one for this peak, and a final one for this peak, because they're separated in time and they have different masses. So when you do sliding window, you can use retention time as a parameter to kind of help you figure out your answer. And that's why this works so well for this, because we have the 3 different peaks. So we want to be able to process the different components. So remember, we couldn't do average over RT, we'd just be able to look at one at a time. We can do the auto peak detection, where it had the blue areas under the peaks, but you can't really control the peak detection on that. So sometimes it works well. In this data set, it works pretty well because the peaks are nicely resolved. But if you have something really complex, like an ADC molecule, you wouldn't know that it's more than one peak, even though underneath that big blob, you do have a lot of different components or different forms or isoforms of the molecule. So that's where sliding window really is extremely powerful at looking at the data and assessing it. So what I'm going to do is, because this is pretty slow, I'm not going to waste time and we can watch this go through. So what it will do is it'll go through, and when it gets to the end, this is going to show you a finalization step, and that's when it's doing the merging, and then it's finished this first file. Then it's going to come down and start the second file, and so you'll see the little window moving across this raw file. And it'll do the same thing, and then it'll get to the finalization where it's merging together the deconvoluted spectrum, and then you'll have your results from this experiment and your results from this experiment. The final merger is bringing the results from these two experiments together into a final results table. Okay, so we have a lot of merging happening here to make sure you kind of keep that straight. What I'm going to do is I'm going to stop it because it is kind of slow. And I'm going to show you one that I've already processed. So in this version of the software, we have a Loads Results tab that's much easier to be able to find your experiments that you just processed. Okay, so when we come in here, this is the one I processed from earlier. Now you remember when we first started this, we submitted the experiments to the queue and the auto peak detection. So those are the results from those two, so you can easily open that up. But let's go ahead and look at our sliding window results that I did earlier. Okay. Now they're in the database. That's one thing. Actually, let me go back and explain that because that's important. Your results are here. They're in your database, in your software. Okay, this is really important. The database lives on your computer, and let me actually show you where the database lives because I do want to make sure that people are aware of this. So in your software, on your computer, this location right here, okay, C program data, Thermo Fisher without a space, is where your database lives for your BioPharma Finder software. If you're going to back up your computer, this is the location you want to back up because everything is actually written into this database, and this is where it's saved. Okay, so that's where all of these results are. It's a little bit different than the previous version. You don't get the SQLite file like we had. It's all part of the database now. Okay, so now let's go back to the process review page. So we're looking at the sliding window multiple file experiment, and now we can actually look at the results. So here you see your two chromatograms, which we saw before, and now we have deconvoluted results. So if we zoom in, we can actually take a look at our results. And so we see light chain, we see the FC, we see the FD, and we also see different glycoforms of the FC region. Remember, so we should have the different glycoforms as well. And you also see the source spectrum here, and they have the blue lines for when it's actually identified something. And let's look at the light chain. That's the simplest one. So we're going to zoom in here. Okay. And now you're going to look at this and you're going to say, well, that looks a little bit crazy. What's going on? Why isn't it marking it on this peak? Right here's the largest charge, the largest mass for the most abundant for this specific charge state. So what it's actually doing is it's marking the monoisotopic mass. In sliding window, the software is going to mark the monoisotopic mass with the blue line. And let me show you that. So if I expand here, and I expand here, and let's see, I need to bring this up a little bit so you can actually see it. Okay. Oops. I think this is the 26th charge state, I think. Okay, so we can sort by that here. Or no, 24th. So the 24th charge state. Okay. So it's actually marking this at the monoisotopic mass. And that's why you're going to see it off the actual ball. In the other version, so if you run this average over RT, you're going to see it mark it here. Or if you do the auto peak detection, you're going to see it mark it here. So that's just something we did different with sliding window. We decided to put the marker at the monoisotopic mass, as opposed to the other ones, we actually put it in the average. So just so you know, don't be concerned about whether the marking is in the wrong place or not. As long as your mass, the actual mass, is correct, which you do want to check that as well. In this version of the software, let's go back to the component level. I want to make sure I show you that before I forgot. If we go back to the component level, you have your monoisotopic mass, you have your CV. Remember, because we have the two different files, we're saying that these, we're grouping these together, and then we can see the CV and the measurement, which is good. We have a theoretical mass, so in the past you didn't have theoretical, you now have the theoretical mass, so you can see what it should be. Your error measurements of the, matching, relative abundance, number of files, number of files observed in, and then here's your conditions. So we have the sum intensity of our condition, and then this shows our CVs as well. So let's see. zoom back out. Let's zoom back out. So one thing I want to show you that's really nice, and I really like this a lot, is, let's zoom in here. Okay, so we're at the component level, we're seeing all files. If we expand down to the raw file level, now we see the individual files. Okay, now here you're seeing base peak, and now you see the abundance trace for the light chain. And if you come down here, you can see the two abundance traces for the two different files. So it really allows you to see what is really happening in your data set. You can also, you can see there, see the different levels, okay? And then the same for the different glycoforms as well. Okay. In the table, you have the same great table that you have in peptide mapping. Please take advantage of these filters. They're awesome. So if we wanted to just look at modifications, which would be just things that have the glycans, quickly do that. Now you see all the different forms. Okay, you can, you really, these filters are just great. If you want to look at the components that we just identified, here's all the ones that we just identified. You can select a few, and you can export them. So you can check that and export just the ones that you selected, or you can export everything. Let me show you how you add a spectrum to the library. So what you need to do to add a spectrum to the library, at the component level, you'll see that the Add to Library button is disabled. Go to the raw file level. Once you're at the raw file level, you can add to library. So we can say that's our raw file if we want, and we can say this is for the light chain. And we say OK, and then we do this, which it doesn't, it's all the same spectrum in this case. And if you can annotate it, basically is what I'm trying to show here, is that you can annotate it however you want. You can go to spectrum comparison, and you can see I have a bunch of different spectrum in my library, and I can choose any two, and then it would actually do the mirror plot for the two different files. And you can pop this out. It is floatable. You can copy and paste and do everything that you could do before. So you can see that there's a few differences in between these two files. Okay, so that's the other feature. One feature I think, let me show you if I actually did show you about this one. The other right click is set as a reference component. Okay, so what is that? So a reference component is what you get. You get, by default, it takes the most abundant one and sets it to 0. And this is the mass difference between all the reference components. So let's actually set this one to 0. And then you can see you're starting to see the different glycoforms. So that's what the reference component for is as well. One thing I forgot is the software, when you're running it in a manual mode, the software does not save your results. So you want to save it periodically so you capture your results, and same thing with the method, so you want to make sure you actually capture that. Okay, well, I hope this was useful, and please check out the other videos that I have for BioPharma Finder 2.0. Thanks.